So today, our mathematician spotlight is Jayadev Athreya. He is an associate professor at the University of Washington. Now you know what that means. He has tenure. He actually got tenure at University of Illinois at Urbana-Champaign, and then got a different job at Washington, and they gave him it with tenure, which answers someone's question the other day, which was, once you get tenure, can you move, and would you have to start over? And you don't always have to start over. So he studies flows on surfaces and billiards, which is similar to what I study. And I just wanted to show you a paper that he wrote recently. So he and this guy, Jayadev Athreya, wrote this paper called A Trajectory from a Vertex to Itself on the Dodecahedron. And the abstract, which I'll read to you because it's quite small, here I'll make it a little bit bigger, says, we prove that there exists a geodesic trajectory on the dodecahedron from a vertex to itself that does not pass through any other vertex. So here's a dodecahedron, and you would want to start at some vertex and make a path that doesn't pass through any other vertices. It just is a nice path that doesn't hit any corners, and then it comes back to the same thing. I had shown with some other people in a paper that there was no such trajectory on a cube. So if you have a cube, you start at a vertex, you have a nice trajectory that doesn't pass through vertices. Well, eventually it might hit another vertex, but it can never be the vertex you started on. There's no such trajectories. But he and David showed that there is one for the dodecahedron. Let me show you the proof. There's the proof. They sort of unwrap the thing and put it on the table. And there's the proof. That's it. That's the whole paper. Here's the end. Boom. So a 2-page paper. Pretty neat, huh? And so since I happen to have a dodecahedron in my office, I put the path on there using their helpful diagram. So it starts and ends at this vertex, and then it goes in a straight line, which you can tell because I use tape, which doesn't bend. And it goes around, it doesn't hit any other vertices, and then it comes back to the same one. And maybe at an angle, so maybe this tape isn't exactly laying on the other guy, but that's okay because it's back to a vertex. So you can have a look at that if you like. You probably want to wash your hands after because it's made of lead. Okay. Let's go like that. Okay, so last time we talked about setting up and interpreting integrals. And today we're going to do the same kind of thing. And the new thing will be that we will see a region where if you put it in a certain order, you have to break it into 2 pieces. So just a few minutes ago, actually, we sketched the region of integration for the integral 0 to 1, root x to 1, 0 to 1 minus y, f of x, y, z, and then it was dz, dy, dx. So here's what it looked like. So we had the z-axis, the x-axis, the y-axis. We drew our little square in the xy plane. It was like a parabola at tangent to the origin, and then coming out here. So this is x, y, z. And then on the back, we had the line z equals 1 minus y. And then this plane, z equals 1 minus y, intersected this curved surface, y equals root x, in a curve that goes from there to there. So this thing looked like we have a sort of a vertical curved thing on the front, and then we have a slanted roof on the right, and then we have the back, which is in the plane of the board, and then the bottom. So it's this sort of curved tetrahedron thing. So our fun task will be to rewrite it in 2 other orders of integration. So let's rewrite it in different orders. So first, let's rewrite it in the order, I'll just write them over here, dx, dz, dy. And then second, let's rewrite it in the order dy, dx, dz. Okay. So let's do the order first. So for the first guy, our outer variables are z and y. So this is going to be our shadow plane. Let's draw the thing first in the yz plane. So here's the yz plane. And we want to say, okay, suppose you had this region R, this solid, you shined a light on it, what would be the entire shadow of the region in the ZY plane? And maybe it's not too hard to see that it's just that back triangle there. So it's just this region here, going from z equals 1 to y equals 1 under that region. And if we're doing it in the order dz dy, that means we pick a fixed y, and we go from z equals something to z equals something. So we go from z equals something to z equals something. Z at the bottom is 0, and z at the top is just whatever the equation of this line is, which we know is 1 minus y. Because that's the plane that we were using. This, after all, is just z equals 0 to z equals 1 minus y, and this plane here at the top is z equals 1 minus y. So let's rewrite that part of the integral. So for the outer part, we're going from z equals 0 up to z equals 1 minus y. And then we want all those vertical pieces from y equals 0 up to y equals 1. OK, now the last thing to do is the x. So we're going from x equals something up to x equals something. So we imagine that we have a point, maybe this point, our favorite point in the yz plane in the back here. And we have a point coming from negative x is like negative infinity, in parallel to the x-axis. At some point, it comes into the solid, and then it stays in for a while, and then at some point, it pops out, and it keeps going. So we want to know which x value does it pop in, x equals something, and which x value does it pop out, x equals something else. So it pops out in the back here, in the yz plane, where x equals 0. And then it pops out along, well, the front here. It can't possibly pop out along this this roof part, because if it was inside the triangle, then it was below the roof. So it pops out along the surface y equals root x. So it pops out along y equals root x, but we want to solve for x. So y squared equals x. So it pops out at x equals y squared. So we want to go from x equals 0 up to x equals y squared. And then we're integrating f of x, y, z, dx, dz, dy, which is what we wanted, dx, dz, dy. Yeah, question or idea? Okay. Good. So then the other order to do is dy, dx, dz. So that means our shadow plane is the xz plane. So I'll draw that here. xz. So that's this plane over there. So you have to imagine somehow that now I'm shining a bright light from this side, and it's projecting onto this, and you know this part is going to be in shadow. But where exactly is the edge of the shadow? So it's some sort of edge of a shadow like this, of the region, but we don't know exactly what it looks like. We have to figure that out. So, good. Whew. So, how do we figure this out? It's written on here somewhere. Okay, so it certainly attaches as z equals 1 and x equals 1. So here's the 1, and here's the 1, and it looks something like this. But what is the equation of this thing? So we know it's the shadow. This curve is the shadow of the intersection of z equals 1 minus y and y equals root x. So it's the shadow of this curve here. Is this curve over there and this curve over here, which I've popped out. And we want to know its equation in the zx plane. So the way to figure out its equation in the zx plane is just to eliminate y. So let's see. So if we eliminate y equals root x, so we get z equals 1 minus root x. So there it is. So z equals 1 minus root x. Okay, and if you want it in terms of x, You could put x on the other side. Root x equals 1 minus z. So x equals 1 minus z squared. I'm missing something. Oh no, we're good. Okay, x equals 1 minus z squared is equals root 1 minus root x. So that's what that thing looks like. Okay, so now we are wanting to write an integral in the order dy dx dz. So z is on the outside. Z goes from something up to something. X goes from something up to something. Y goes from something up to something. F of x, y, z, dy, dx, dz. So let's figure these out. So z, let's see. If we pick our favorite z, here it is, and then x goes from something up to something. So we go from x equals 0 up to whatever x is on this curve. And we figured that out. X is 1 minus z squared. So x goes from 0 up to 1 minus z squared. And then which ones of those do we want? Well, we want all the way from z equals 0 all the way up to z equals 1. Okay? And so we have our whole double integral shadow plane figured out. So now the last thing to figure out is y. So if we pick our favorite point in the zx plane, maybe this one, we imagine, okay, that's here. So now we imagine something in the y direction coming from negative y. It comes in, it pierces in somewhere, it stays in for a while, and then it pops out. So it looks like it pops in. This should be straight and horizontal. It pops in here on the surface y equals root x, and it pops out here on the surface z equals 1 minus y. So we just have to solve for y. So y equals 1 minus z. So this pops in at y equals root x, and it pops out at 1 minus z. So there we go. So we can set it up in several different directions. Yeah. Oops. Yeah, good. Okay, good. Yeah, questions or ideas?
But if you found the shadow like going that way, would you do like it popping in on the 1 minus z plane and then out on the other one? Would you switch?
With which, in this direction, or this direction?
Like the shadow, like that side.
This side?
Yeah.
So we would make our shadow in either the xy plane, the xz plane, or the zy plane.
So if you like looking this way versus that straight?
If you made it looking this way instead of that way, it would be the same shape, but you would just take your picture here and you'd flip it over like a mirror image. Yeah. I sense you're not satisfied.
So just like would the bounds be switched then? Because if you chose a point on that shadow and then we're going into the shape.
Oh, because they would be switched. So you always have to start in the negative direction and you move to the positive direction. You're going always in the positive, like positive x direction, positive y direction, positive z direction. Yeah. Okay. 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 So, our next quest is to rewrite some kind of an integral. What is it? 0 to 1, 0 to x, 0 to 1 minus x squared. Oh, this is 1 minus x. 0 to 1 minus x of f of x, y, z. And then dz, dy, dx. In the orders let's see, dy, dx, dz, and dx, dz, dy. Okay, So you could notice that we're given one where the shadow plane is the xy plane, and we're being asked to redraw it where the shadow plane is the xz plane and the yz plane. So there are 6 total orders of integration because there are 6 ways of rearranging 3 things, but only 3 different shadow planes. So we're going to do them all. Okay, so the first thing to do is to sketch the region. Always draw a picture with the order that we're given. So that's like a fun game to play. So maybe we add on here x equals 0 to x equals 1, y equals 0 to y equals 1 minus x, and z equals 0 to z equals 1 minus x squared it was supposed to be. Okay, let's do it. So our shadow plane is the xy plane. So let's draw it as given. X is going from 0 to 1, and y is going from y equals 0, I know what that looks like, to y equals 1 minus x. I know what that looks like. It's a line of slope -1 starting at 1. And then let's see, if you fix an x, you're going from y equals 0 to 1 minus x, so we have like vertical pieces here. Okay, that's our region. And now we want to draw this, like figure out what's going on here. So let's draw it in 3D. So I suggest making the whole box and then drawing the whole box in your 3D picture, and then drawing whatever you need. So here we need just a triangle that's close to the origin. So here's our triangle. Good. And I drew vertical stripes. So here's the vertical stripes. Okay. And now we think about z. So z is going from 0 to 1 minus x squared. Here's z. So 1 minus x squared starts at 1, and then it's a downward facing parabola in the zx plane. So the zx plane is this back left plane here. So in this plane, it's just a parabola. So it kind of goes like that. And we don't need this back part, so I'll erase it. And then z equals 1 minus x squared, so x is 0 in the whole zy plane. So it's just z equals 1 in the whole zy plane. And we cut off here at y equals 1, so the back looks like that. And then again, you have to sort of imagine what's going on. So we imagine that we are cutting off along this y equals 1 minus x line here. We have like a vertical plane. And then at the top, we have this curve, sort of like a half plane or a tunnel. And so imagine how this and this thing come together. So in this case, so it's just some kind of a curve. So that goes from here to here. So the roof is made by the parabola z equals 1 minus x squared. And then the front here is like a wall, just a regular wall, made by y equals 1 minus x. So there's our region. There it is. And now we have to just write it in some more orders. Okay, so for the first order, okay, so first order, this guy. So we want to write this in the order dy, dx, dz. So our goal is to have some kind of integral where we're integrating f of x, y, z, dy, dx, dz. So we want to go from y equals something up to y equals something, x equals something up to x equals something, and z equals something up to z equals something. So that's the setup. That's what we need. Okay, so our aspirational shadow plane is the xz plane. So let's draw the xz plane here. How much of it do I need? Just the positive part. So x and z. Okay, so the xz plane is like this left plane over here. Maybe it's a little bit confusing because on the board, it's sort of like we're looking at it from the back. So the positive x-axis goes to the left. Whereas over here, I'm drawing the positive x-axis going to the right, which is how we usually draw it. So you just have to imagine this picture just being turned around so that the z and the x are in the way that we usually have them. So now we shine a bright light onto this, and we see what is the shadow of our region on the xz plane. Can you see it? What it should be? Yeah, it's just this part. It's just like this shadow of the roof. So it's just this z equals 1 minus x squared. So I'll draw this. Here, we're trying to hit, starting at z equals 1, ending at z equals 1, the parabola z equals 1 minus x squared. Looks something like that. And we're going from, let's see, we're integrating with respect to x first, so holding z constant. So we go from z equals something to z equals something. Oh, so we go from x equals something up to x equals something, holding z constant. So I can see that x equals 0 over here on the left. And now x equals whatever it is on this curve. So we got to solve for x. Okay, so let's see, x squared equals 1 minus z. So x equals plus or minus root 1 minus z. And here x is positive. So it'll be the positive square root. So x equals the square root of 1 minus z. So we're wanting to go from x equals 0 up to x equals square root of 1 minus z. And then we want all of these things from z equals 0 at the bottom all the way up to z equals 1 at the top. So we go from 0 to 1 in the z. Okay, just one more thing to do. So we pick our favorite point in the xz plane and figure out what y's we need. So that point is like on the left side somewhere, like maybe there. And we imagine that we start with some y value in negative infinity, and we come in the positive y direction. So our point comes in, it pierces into the solid here, it stays in for a while, and then it comes out there. Now it's not in anymore. So we have to figure out where it goes in and where it comes out. So what y value it has. So here, where it comes in, it has y equals, can you figure it out? 0. Yeah, 0, because it's just the xz plane where y equals 0. So it comes in at y equals 0, and then it comes out, well, on this green surface. And actually, we already have that equation in terms of y. So it comes out where y equals 1 minus x. Whatever this green surface is, the green surface is y equals 1 minus x. So it comes out at y equals 1 minus x. Yeah. Okay. Good. Okay, for the other order of integration, I'll just use the same piece of board. So for this order of integration, we want dx, dz, dy. So we want to set up an integral of f of x, y, z, dx, dz, dy. So we're going to want to go from x equals something up to x equals something, z equals something up to z equals something, and y equals something up to y equals something. Okay, so the shadow plane we want is the yz plane. So let's draw it. So that's the back here. It kind of already is drawn in the same perspective. So we want to know, what is the shadow of this plane on the back? Well, it's just the square. It's just the whole square, the whole 1 by 1 square. So y and z here, it's that whole square. So if we want to go, yeah, we would just go from y, whatever. See, they both go from 0 to 1. Great. Okay. Now, we pick our favorite point in this place. Like maybe this is our favorite point. I'll change my color. And then that is here in the back. And then we have to figure out for our favorite yz point what x values we need. So our x comes from like negative infinity. It's coming in parallel to the x-axis. It pierces in at the back where x equals 0, I guess, because it's in the yz plane. And then it comes out on this surface. So it's in for a while, then it comes out on the surface, and now it's out again. So I guess we should go from x equals 0 up to whatever this surface is, z equals 1 minus x squared. So solve for x. So let's see. We have z equals 1 minus x squared. Did we already do this? I guess I erased it. So x squared equals 1 minus z. X equals square root of 1 minus z. There. But you should be a bit nervous because perhaps your favorite point is not the same as my favorite point. So my favorite point was up here, but maybe your favorite point is over here. So for this point, let's see, that is located approximately here. If we have something parallel to the x-axis, it comes in at the back where x equals 0 as before. But then when it comes out on the green plane. So for your favorite point, this should have been, let's see, if y equals 1 minus x, then x equals 1 minus y. Should have been x equals 1 minus y. So something is horribly wrong. So we have to break it into two pieces, it turns out. Okay, so we have to figure out what the shadow of this curve is in the yz plane. So it's something like this. And then we'll have to make two integrals. One for the yellow part, and then one for the blue part. So maybe I should, actually, it would maybe be clearer if I made these white and green, because those are the colors where they pop out. So here's white, and green, the colors where they pop out. Okay, so we have to scrap this a little bit and fix our lives. So let's see. So let's just define the places where things do work, like my yellow point here. So if you're popping in at x equals 0 and out on this top thing, then you're above this curve here. So we need to define this curve in the yz plane. Okay, so that's the intersection of z equals 1 minus x squared and y equals 1 minus x. And in the yz plane, there is no x. So maybe the thing to do is to solve for y and plug into the other. Let's solve for x and plug into the other. One of these is easier to solve for x than the other. So it's the intersection of z equals 1 minus x squared and y equals 1 minus x. So let's solve this for x and plug in here. We could also alternatively solve for x here and plug in there, but it's got a square root, so why would we do that? So x equals 1 minus y, and then plug into here, so z equals 1 minus y squared. So this curve, we have just figured out, has the equation z equals 1 minus quantity 1 minus y squared. Now we know. You could multiply out, but why? Don't do it. Okay, so now let's set this up. So the time when we're in the white region, where we pop out on the curved white roof, is anytime, let's see, if you are picking a fixed y value, this one, you pop in z equals 1 minus y squared, so 1 minus y squared, and you pop out at z equals 1. So there's that. And then that's when you go from x equals 0 up to x equals square root of 1 minus z. So that's good. Good? Okay. But then we also need the bottom part. So for the bottom part, let's set up the integral. So for these, we would also want to go from y equals 0 up to y equals 1. But for these, if you have a fixed y, your z goes from z equals 0 up to z equals 1 minus y squared. So you go from z equals 0 up to z equals 1 minus y squared. And now your x goes from x equals 0 up to x equals 1 minus y. And then f dx dz dy. So the idea there was in two of the orders, the order that we were given and the second order that we did, it was just one integral. But for our third order, actually there was a curve that cut the two pieces and we had to define them separately. Questions or ideas? All right. All right. Good. Make sure I have enough minutes left. How many do we have? 13. That is a lot. Don't worry, we won't use them all. Okay. So, good. Okay. So, as our last example, let's set up a triple integral. In this case, we're not going to be given the bounds of integration, and we're not going to be given a picture. We have to figure it out. So, set up a triple integral over the region bounded by, let's see, the xy plane, the yz plane, and then two special planes. So the plane x plus y plus z equals 1, and the plane x minus y plus z equals 1. Okay. So the first thing we should do is probably draw a picture. Always, always. I know what the xy plane looks like. It's the bottom. Good. I know it. Let me label my axes. Good idea. So the xy plane is the bottom here. The yz plane is the back there. But these planes, we have to figure out what those look like. So the best way, I think, to find out what a plane looks like is to plot some points on it. So let's do this one first. So for x plus y plus z equals 1, just find, so there's 3 points to find a plane. So 3 points. I can think of some easy ones, yeah? Like if y and z are both 0, we get 1. So you get 1, 0, 0 is a point on it. And then if x and z are both 0, y is 1. So 0, 1, 0. And similarly for z, 0, 0, 1. Oops, 1. These are all points on the thing. So if I let this be distance 1, I would get 1, 0, 0, 0, 1, 0, and 0, 0, 1. So those are all on this first plane. Okay, let's do the second plane. So for this plane, x minus y plus z equals 1. The first and third points still work. I still get 1, 0, 0, and I still get 0, 0, 1, because those both have 0 for y, so the negative sign doesn't change anything. But then if I let x and z equal 0, I get negative y equals 1. So 0, negative 1, 0. So for this one, I have two of the same points, but then I better add in a negative y-axis here, because I get negative y, negative 1 here for y. So the second plane is that there. So I've drawn this in perspective, but these planes are kind of the same. So they're symmetric across the xz plane. Okay, and then this is also bounded by the yz plane in the back and the xy plane on the xy plane on the bottom. So you can see sort of what it looks like. It's a tetrahedron, but not a regular tetrahedron. Okay. So this question didn't tell us what order we have to do it in, so we can do it in whatever order we want. But I don't know about you. Setting up two integrals the last time was a bit onerous. Perhaps we don't want to do that. So let's see. If we did this with our shadow plane being the xy plane, then a z coming in from the bottom would come in at z equals 0, but it would come out at two different places based on whether it came out on the orange plane or the yellow plane. So maybe the xy shadow plane, maybe that one would not be so good because it requires 2 integrals. Okay? How about the yz plane? So suppose we did the yz shadow plane. Then an x coming in from the back would come in at x equals 0. But again, it would come out at different places based on if it came out on the yellow plane or the orange plane. So again, it's not, I mean, it would be just fine, but it would require 2 integrals. So to make our life easy, perhaps we should try the xz shadow plane. Because if we use xz as our shadow plane, then everything in the positive y direction will come in on the yellow plane and go out on the orange plane. So let's try something with the xz as our shadow plane. So using xz as our shadow plane, let's do this. Oops. Here I think I actually need, oh, who knows. Let's draw a nice big plane. So here's x and here's z. So again, in the picture over here, the positive x-axis goes to the left, but you imagine sort of turning it to the right to make this picture. So I have the points 1, 0, 0, and 0, 0, 1. And the yellow and orange planes both go along that line. And the shadow of this region is just the triangle underneath that. So our region is in here. And that is this right here. So let's set up an integral for that. So we can do x on the interior integral or x on the exterior integral. Do you have a preference? I don't care. Let's do x on the, let's see, well, what is it on the sheet? It's x goes from something to something with z fixed, so z is on the outside. Okay, so we'll do horizontal slices. So we go from x equals 0 up to x equals whatever it is on this line. So this is the line from 1, 0 to 0, 1. So this is z equals 1 minus x, or x equals 1 minus z. Those are the same. So this goes up to x equals 0 to x equals 1 minus z, and z equals 0 to 1. So that defines the shadow region. And now we just have to think about what happens with a point in the y direction, because we want to figure out y goes from something to something. So if you have some y point, we have some point, our favorite point, maybe it's this one in the xz shadow region. And now we imagine a point coming in from the negative y direction. It pierces into the solid somewhere. It stays in. It visits its friend in the shadow region. It stays in for a while, and then it comes out again. So it comes in on this yellow plane. So it comes in on the yellow plane, x minus y plus z equals 1. And we want to solve for y here. What's the y value when it comes in? So let's solve this plane equation. So that would be x plus z minus 1 equals y. Okay, so y equals x plus z minus 1 is where it comes in. And then over here, it exits on the orange plane, x plus y minus z plus z equals 1. So if we solve for y, we get y equals 1 minus x minus z. So it comes out at y equals 1 minus x minus z. So let's put those in. It comes in at y equals x plus z minus 1, and it exits at y equals 1 minus x minus z. And then we'd integrate our function, f of x, y, z, dy, dx, dz. So in this case, we had to figure out what the region looked like and write the integral with the bounds of integration. But you're able to make it happen. Okay. And as a final challenge, let's suppose that we just violently slice this tetrahedron. So we come at it with the plane z equals x. So I'm going to erase some of the scratch work that we did and draw a slightly new picture. So imagine you have this sort of the same region, but now you want only the part of it that's below the plane z equals x. Okay, so z equals x as a line is like y equals x type of line. So it meets this thing. So it's just like the forward part of this. We just sliced it in half that way. So let's try to write an integral for this. So shall we keep the same plane? The xz plane? Let's keep the same plane. So again, that same line, it can't be outside of that. But now it was cut by the line x equals z. So now our region is actually, hey, only this bit in here. So we have to set it up for just only this bit here. So we have two options. One is to do vertical sections, and one is to do horizontal sections. And last time, you did not have a strong opinion, because it really did not matter either way. But now, perhaps you do have a strong opinion, because you prefer to write one integral instead of two. If you were to use vertical segments, you'd have to do one integral for the left bit, where it goes from the white axis up to the blue line, and a separate integral for the right bit, where it goes from the white axis up to the yellow and orange line. So that would be two integrals. So maybe you don't want to do that. Maybe you would rather use horizontal, where we go from x equals something up to x equals something. Because then we'll only have to write one integral. So let's try to do this. So this means that z would be fixed. So we'd have an integral from z equals something up to z equals something. And then x would go from the blue line to the orange and yellow line. And then I think y would do the same thing as it did before. So unfortunately, I erased them, but luckily someone has noted it down. Y goes from x plus z minus 1 up to 1 minus x minus z. We just have to figure this out. So if z is fixed, x goes from this blue line, which is z equals x, so x equals z, up to this line here, which was z equals 1 minus x, or x equals 1 minus z. So x equals 1 minus z. And then z goes from, well, let's see, we only want these z's. So z's from here to here. Can you figure out what this intersection point is of these two lines? So we want to intersect z equals x and z equals 1 minus x. Totally got this. Another way of thinking about it is that we had the 1 by 1 square, and we just made an x. So we want to know what the coordinates of the center of this 1 by 1 square is. So it's just a half a half. You can check that if z and x are both 1/2, both of these are satisfied. So z goes from 0 up to a half. And then we have f of x, y, z, dy, dx, dz.